All right, so I guess we're officially recording the first set of notes. I didn't realize that I hadn't recorded any from this unit, even for my seniors, but you know. So the fundamental theorem of calculus. In order to pull this off, what we're gonna have to do is look back at what we did last week on Friday. And what we were doing was basically finding the antiderivative of a bunch of stuff, right? And especially A, C, D, and F, which were all just things that had regular old exponents, x's with exponents. The end result was that you bumped the exponent up by 1, and then you just threw the reciprocal of the new exponent on the front. Took this exponent of negative 1, bumped it up by 1, threw its reciprocal on the front. Reciprocal of 1/2 was 2, right there. Now this one already had a 2 on the front, so when we bumped this exponent up to a 6, we had to put a 1/6 in front of our 2, which reduced to the 1/3. But the same thing is happening here. Took the 1/2, bumped it up by 1 to a 3/2, threw the reciprocal 2/3 in front. So when you're dealing with x's with exponents, other than this kind of thing, because this is technically not an exponent, that's going to be 1 over, any constant over linear is always going to be an ln. But if you're dealing with any other powers of x, you're just going to bump the exponent up by 1, put the reciprocal of the new exponent on the front. Boom, that's it, okay? That's how we do that stuff. So then for today, we're going to use that shortcut of bump the exponent up by 1, throw the reciprocal on the front to talk about the fundamental theorem of calculus. So the last time, what I did was I defined the integral as a tool that is used to find the area under a curve. Okay, well that is only true if the entire portion of the curve you're talking about exists above the x-axis. Why is this box here? What is that? Okay. So for now, we're just going to assume our curves are all 100% above the x-axis, so I will define the integral as being the area under the curve. And what you're going to do is simply find the antiderivative, which we'll call capital F of x, and then you just evaluate capital F for B, capital F for A, and subtract. The antiderivative is right, no constant.
So it's without the C at the end.
Without the C at the end, which we technically have not learned yet, but yes. Okay. So yeah, all you're going to do is find the antiderivative and then evaluate using your limits of integration. That's what this A and B are called, and you subtract. And it's always end minus beginning. If you're not sure why, go, well, think about it. If we started at 2 and we ended at 10, how far did we go? 8. You see, you got that number by doing 10 minus 2. It's always end minus beginning. Evaluate, subtract, evaluate. Just like that. And that will be the area under the curve between those two x values. Yes? Yes, it is that simple. I could demonstrate for you really quickly why it's that simple.
Yeah.
Okay, all right. No, I'm talking, this is going to be remarkably simple. You ready? Are you choking, Krill?
I'm fine.
Try not to die when I'm recording the video, okay?
A little piece of bread.
Okay. We almost lost the student on video. If I monetize that, you know how much money I'd make monetizing that? All right. So can we agree that this is the what? Can we agree that this is the line y equals 2? Great. Oh, maybe if I put some numbers, there we go. Okay, now from x equals 1, 2, 3, there. Can we also agree that the area of the rectangle that I just created from 0 to 3 is just 2 times 3?
Yes.
Great. How about instead I say the integral from 0 to 3 of 2 dx, because this is my function. Well, right now it doesn't have an x, so that is technically an x to the 0 there. Can we all agree to that? So when I bump that 0 up to a 1, now there's an x, right? And the reciprocal of that new exponent is just a 1, so I don't need to change anything, and I'm going to evaluate that from 0 to 3. This is one way we show the evaluate. And what it says to do is plug in, subtract, plug in. 2 times 3 minus 2 times 0, which is 6. So that is how you find the area under a curve from A to B, as long as that entire portion of your function exists above the x-axis. Pretty neat, huh?
Wait, where'd you get the 2x from?
That's the antiderivative of 2. Think about it. Yeah, I mean, what's the derivative of 2x?
Um,
It's 2, right? So this is its antiderivative.
all right.
So that's what we're doing today. Whee!
So, wait, how does that reflect on the curve?
This is your curve.
That's a,
All functions by definition are called curves.
so it doesn't matter if it's like a straight curve or curved curve?
Why would the rules change? Math is
No,
math.
It just seems kind of.
Math is math.
But it's like, so it took like.
It's easy. Allow it.
It took humans 12 millennia to figure.
It's
something
easy.
out that simple.
Allow it. Okay. So we're going to call this the definite integral because it has limits of integration. And specifically, a moment ago, Zach, you asked if that's going to get the plus c. Well, no. When you have limits of integration, there's never a plus c. Ever. Because it ends up canceling itself out if you include it. When you do the subtraction, it'll cancel. So because of that, we don't even bother with it. What I have here is just a table of things that describe properties of the definite integral. And they're pretty self-explanatory. I'll tell you a couple of them that are really super duper important. Let's see. First of all, if you integrate a function and you go nowhere, then clearly there wasn't an area. Okay. This is one that you just saw me do. I used this property where the constant was 2. So this would have been 2 times 3 minus 0. So if you integrate a constant, it's really just that constant times the difference every single time. This one is super important. Put a star next to it on both sides. It says that if you switch the limits of integration, you will change the sign, the sign, on the value of the integral. If you switch the limits of integration, it switches the sign on the value of the integral. Let's say for example, if I had evaluated this from 3 to 0 instead of 0 to 3, my answer would have been negative 6.
What the area is the same?
I'm telling you about the properties of a definite integral. I did not mention area when I said that. Just go with the flow, please. If you switch the limits of integration, it will change the sign on the value of the integral. Okay? Okay. This one, super, super important. We will use it constantly. It basically says, yo, if your function has a constant multiplier, you can either integrate and evaluate, or you could factor out. It's almost like factoring out. You can move that constant out to the outside, and then integrate and evaluate, and then just multiply by the constant. We did things like that when we were doing summations. Because if you think about it, integral is just a fancy summation. That's all it is. It's just adding up an infinite number of skinny rectangles. So this property was true for summations. It's true for integrals as well. These constants can be brought to the front. This one was true for summations. It's true for limits, so it's true for integrals. It's like a transitive property of integration, if you will. This one says, hey, f of x, if I integrate it from a to b, and I integrate it from b to c, and I add, it's the same as going from a to c. I mean, that should be pretty obvious. I mean, again, if I said, oh, well, let me chop this thing up, and for some reason I want to go from 0 to 1, and then want to add from 1 to 3, it's going to be the same as going from 1 to 3, or 0 to 3, you know. And this one, which we will use sometimes, but it's really important. It ends up being more of an intuitive thing. It just says that if you've got a bunch of things strung together, pluses and minuses, you can make that several integrals that are strung together with the same pluses and minuses. Remember when I was talking, I call it spot derivatives? You use this concept for like a spot integration. If you have a polynomial, and you just basically quote unquote integrate at each term. It's this idea, even though I'm not writing it out. Cool? These two, big time important. It's not like memorize the formula, it's just know that they're true. We will use this one a lot. That will be big time important soon. Okay? All right, so we're going to use the fundamental theorem of calculus to find the area between the y-axis, the function y equals x squared, and we're going to do that from 0 to 1. And it's not necessary that you have a picture because the way they set it. But, you know, I'm just going to go ahead and draw the picture, a quick sketch. And that's because I specifically said as long as the entire region is above the x-axis. So I just want to make sure that that entire region is above the x-axis or at the x-axis, just not dipping below. So the function is x squared. Well, that's pretty easy to deal with. So for a, we have y equals x squared. We're only going from 0 to 1, so I really only need quadrant 1. Well, when you evaluate at 0, x equals 0, you get 0 squared or 0, right? So our vertex is at 0, 0. And then we only have to go to x equals 1. And when you square that 1, you get a 1. And it's a quadratic, so it's not a straight line. We know it's curved. So yeah, picture not on a scale. So what we know is that this entire region exists above the x-axis. So we're definitely able to just say the area under this curve. But it does say between the x-axis, this function, x equals 0, x equals 1. So this is the region, we'll just call it region R, that we're finding the area of. Area is the integral from 0 to 1 of y equals x squared dx. We're going to use that shortcut that we basically figured out on Friday and then recapped earlier, is that all you have to do is increase this exponent by 1. So now it'll be an x to the third. And you put the reciprocal of its new exponent on the front, which is going to be a 1/3. And we will be evaluating that from 0 to 1. Another way that you'll see this done, so I'll go ahead and show you that way also, it looks like this. And to be honest with you, I've moved back and forth between the straight up and down bar or the brackets. I don't know why. It just happens by accident.
When I first see that, I think it's notation.
Yeah, I know. So, but it's other places around the world use this notation. Here we pretty much stick to straight up and down. But as long as you recognize what you were doing with it, you're fine.
So where's the S?
S?
Yeah, the S.
You mean the integral symbol?
That's an S.
It's an integral symbol. Do you think these are S's?
Yes, so the type of long S.
No, it's an integral. Anyway, I found the antiderivative, which means I have a definite integral. It's gone. Hey, Zach, what's the square root of 25?
Square root of 25?
Yeah.
Oh, that'd be like, I don't know, like, 4,000.
Well, I said square root of 25.
Oh, square root. Oh, 5.
Where'd your square root bar go, Zach?
What do you mean?
What do you mean? You understand what I'm getting at here? You used the symbol, right? This symbol got to do its job, right?
Yes.
So you stopped saying that symbol, didn't you?
Yeah.
This integral has done its job when you're x squared.
Oh, so you're just representing the one of the pre-indicated that represents it.
1/3 x to the third is the integral of x squared dx.
Okay, now what do we need the brackets for?
The bracket was just the same thing as me saying straight up and down. This means evaluate. I'm not done. This means evaluate. It means sub in the first limit of integration and subtract you subbing in the second limit of integration. There. The bracket or the straight up and down line, they mean the exact. Here, I'll even show you. On my notes, I have one's a bracket and the other's a straight up and down line. Like I did both. In this one, I didn't even draw the second bracket. There's so many different ways to represent, and all it's telling you to do is plug those numbers in. That's all it's telling you to do. And evaluate. Like evaluate and subtract. That's all it's asking you to do. So as it turns out, the area under that curve, 1/3.
That was cool. I understood that.
Pretty neat, huh? Yeah, and honestly, I think that this makes a huge difference seeing this. You know, it's like, yeah, obviously it's a rectangle. I can trust this. You know, this isn't a proof that it's true. It's a, it's more of a proof of concept. Like, look, it's working. You know, yeah, that is okay. Let me ask you this: what's the derivative of that? Well, you bring the 3 down, right? And you'd have 3 times 1/3, which is 1. But you'd have to subtract 1 from that exponent, you get x squared, wouldn't you? So what we did is we just did that process in reverse. So instead, because we're finding an integral, and remember these two things are one symbol, the integral symbol and the dx, they go together. And so when one goes away, the other goes away. And instead of dropping the exponent down to the front and subtracting 1 from it, we're adding 1 from it and dividing by the new exponent. No, no, it's fine. This is important that you understand these things. Okay, part B. Again, a picture isn't necessary, but I'm going to go ahead and draw it just to demonstrate that yes, we are going to exist 100% above the x-axis or on the x-axis, of course. This one's actually just 100% above. Picture not drawn to scale. Square root graph, we're going to go from x equals 1 to x equals 9. Here's a 1, here's a 9, because I said so. And we're going to evaluate, let's see, the square root of 1 is 1. And the square root of 9 is 3. So we're going from here to here. And we know it's not a straight line. We know it's a curve. Now, clearly, I've exaggerated it. But what we were trying to do is find the area of this region. We'll call that region R again, because why not? I do that because on the IB exam questions, a lot of times they'll be like, oh, we'll label the region R and find the area of region R, basically. Okay, we're going to find the area of this structure here. And we'll do that by integrating. Do I want to use blue this time? I'm thinking pink. Amazon Basics. This area is the integral from 1 to 9 of, you know what, I'm not going to say the square root of x. I'm going to say x to the 1/2 power. Because that'll be a lot easier to use the whole bump the exponent up by 1 with the reciprocal trick. That'll make life a lot easier. So now I'm going to find the antiderivative or the definite integral of x to the 1/2. We're going to raise this exponent by 1. So 1/2 plus 1 is 3/2. So x to the 3/2. And the reciprocal of its new exponent is 2/3. And the reason why we're using the reciprocal is because we are trying to undo what this is going to do when you try to find the derivative. So when you try to find the derivative, the first thing that's going to happen is this 3/2 will come down and multiply to the 2/3, become a 1 now, and you get this back. And we are evaluating this one. I'll use a straight up and down line from 1 to 9, and I'm only doing that so that you can see it really doesn't matter. But, you know, this is kind of tough, this whole evaluating with these rational exponents. So when I'm forced to evaluate, I typically will turn my rational exponents back into radicals. That's just easier for me to deal with. So equals, and this x to the 2/3, let's see. Well, what I'm going to do is I want to write it as a radical. This is going to be the square root, because that's what the 1/2 means, cubed. Like that. And that's what we're going to be plugging in 1 and 9 in. Alrighty, let's plug her in. So I have 2/3, and I'm plugging in 9, so I have square root of 9 cubed, and then minus 2/3 square root of 1 cubed. My math is going to have to get skinny. Alright, so square root of 9 is 3. 3 cubed is 27. 27 times 2 is 54. 54 divided by 3? 18. And then this one's just minus 2/3. So instead of calling it Instead of saying it's 17 and 1/3, I'm gonna write this as an improper fraction because I hate mixed numbers, because yuck. And see, it's 52 over 3, right? Yeah. There. Oh, you know what? That was stupid. We should have just left it right here. 27 times 2 is 54, because we should have seen common denominator. Worked way too hard. So this would have been 54 over 3 minus 2 over 3. That was the smarter way to do that. I didn't even catch it. Okay. Do you guys have questions on that, or is it pretty straightforward? Oh, we have a question on that. Yeah. So,
just to confirm.
yes, we're
I'm
confirming.
understanding this correctly.
Yes.
So to get the understanding of the area for a specific area, underneath the curve,
Yep.
like that, in reference between that and the x-axis, limited by in terms of x on the
Yeah.
stuff. So basically, you just have to get the antiderivative of the equation and then just plug in the numbers for the borders of it and put the
And subtract.
last one up in front and minus the first.
Yeah, it's always end minus beginning. Yeah, because you think, like I said, if you started at 2 and landed at 10, you went 8, right?
All right.
That's because 10 minus 2 is 8. It's always end minus beginning.
And that's the exact. That's just what.
That's the exact area.
And that's all I have to do.
Yes, that's all you have to do.
I feel like there's some sort of catch or something.
There is not a catch. That's legitimately it. That's it. That's it. But then there's the catch. No, I'm kidding.
Polynomial.
There's no catch. Okay, so we're going to do it again, only this time we're dealing with a polynomial. Now, again, it wouldn't be in this note set unless the entire region was above the x-axis. But just to confirm, I'm going to go ahead and see what's going on here. Okay, here's what I could tell. First of all, there's a very weird space after that y. I don't know why that's there. That's odd. Well, anyway, what I know is that this thing factors. This quadratic factors. Y equals, I'm going to pull a -6 as a GCF, -6x, excuse me. And it'll leave me x minus 2. Wait a minute. Wait a minute. Something's wrong. Okay, I just figured out what the problem was. My version of the notes over here on the side, which by the way is the notes that I did with the seniors a little while ago, about a month or so ago, has a different equation here. And I just figured out why this equation looks so odd the way it is. It's because I edited the PDF instead of trying to recreate the entire wheel. I just edited the PDF, which means when you edit PDF, sometimes they do weird things. It threw that extra space in there. And the reason why it's different from what I had for the seniors is because after I did the example with them, I wasn't happy with it. So I changed it. Okay, so aneurysm averted. There we go. So what do we see? We see a function that is going to cross the x-axis twice. It's going to cross it once when x equals 0, and it's going to cross it again when x equals 2. Well, that's good because we're going from 0 to 2. And because it's a negative quadratic, it's a frowny face, right? So what we have is a quadratic like this. And then something like this. There. I don't even need to know what this y value is. It's unimportant. I just needed to know, does this entire region exist above the x-axis? And the answer is yes, it does. This is the region we're working with here. So the area of our region, what color have I not used a whole lot today? But yellow's reserved just for canceling things because it's hard to see. The area will be the integral from 0 to 2 of your polynomial function. Don't try to do it with this. Use this. Because then we could use this rule right here that allows us to do quote-unquote spot integrals. It allows us to break polynomials up into tiny integrals that are strung together with pluses and minuses. And you notice how they keep the same limits of integration. So that's what we're going to do here. Alrighty, let's see what this equals. This exponent on this x is to bump up to a 3. There's already a negative 6 sitting there. But we know that when we bump this exponent up to 3, it's going to require the reciprocal of the new exponent in front of it. Like that. And then again, there's already a 12. This exponent on this x has to bump up from a 1 to become a 2. But now we need the reciprocal of that new exponent on the front. And that thing we are going to evaluate from 0 to 2. So I'm just going to clean this up. Negative 6 over 3 is negative 2. And half of 12 is 6. There we are. Let me tell you why I love evaluating polynomials from 0 to anything. Yeah, because the 0 is always going to cancel. It's really nice. I mean, if you're cool with it, I really don't have a reason to plug 0 in. I'm just going to not bother because I see that when I plug it in here and here, it's going to go to 0 either way. So this thing's area is strictly equal to what you get when you plug in the 2. Negative 2 times 2 cubed plus 6 times 2 squared. That gives me negative 16 plus 24, which is 8. Ta-da! It's quite the satisfying answer. An area of a curved region who has an integer answer. You know, because we're so used to irrational numbers with curves because of pi and things like that, but this isn't a circle. And that's it. Pretty easy, isn't it, guys? Awesome.